Okay, what is it? Okay, you just do this one.
Okay. So, see. Good afternoon, dear colleagues and participants of the conference. Today I'll tell you about my work. It started since 2070. Nowadays it's a big work with a lot of articles and papers and patents in Russia, and I work in field of organic chemistry and in field of heterocyclic chemistry especially. We develop new modern fungicides. It's drugs for treatment of fungal diseases of human. Sometimes fungicides are used as crop protection. And today I'll tell you about azoles. Azoles, it's commonly used drugs. It contains this heterocycle 1,2,4-triazole, its pharmacophore group, and some other heterocycles. For example, fluconazole and voriconazole is antimycotics. They're using in medicine, and difenoconazole is crop protection drug. Now you can find a lot of interesting molecules at the drug market. For example, containing 1,2,3-triazoles, 1,3,4-triazoles, and some other heterocycles. I know that the conference is connected between optic systems and organic section. Then I have to talk about the mechanism of action of these drugs. Azoles is a drugs which using they blocking demethylase CYP51 stage, and they are blocking ergosterol synthesis. It's very important strain of fungi, and if you will block this stage, they will die. For example, in protein data bank, you can find a lot of structures of proteins. For example, active site of CYP51 with lanosterol. Hem, it's yellow lanosterol, blue heteroatoms of hem, green, orange is ferrum, and oxygen is red. It's obvious process in our in cells of fungi, but if you will block this stage, for example, by fluconazole, we stop this process and kill some fungi cells. I think it look like a big snake catch some small monkey and block this big enzyme system. If you will look at modern antimycotics, they contain three important parts. For example, pharmacophore group, linker part, second heterocycle, and sterol emulating substitute. It's branch structure. But we decide to create a linear structure and investigated system. For example, this linear structure can be shown like this one with pharmacophore 1,2,4-triazole, one more second heterocycle, and sterol emulating substitute. I think it's a big snake with three parts. For example, head is pharmacophore group, uh, main part is second heterocycle and sterol emulating tail. One of the first works was devoted to the synthesis of oxidazole by condensation of this hydroxide. At the left side of slide, with carbon sulfide in the presence of base, it after this acquisition we can obtain oxidazole and then after the alkylation in the presence of triethylamine and acetone we obtain 14 examples of this compound, which contains three main parts. Next interesting block was diazotyls. The synthetic route was similar. At the first stage, we synthesize some salt, then condensate it in the sulfur acid presence to diazotyl, then alkylation process. In a lot of systems, for example, not only triethylamine DMF, for example, sodium carbonate, acetone, and some others. Some more interesting substrate is 1,2,4 3 tiones. They can be synthesized by the condensation of TSME carboxyles in the presence of base, for example, in sodium hydroxide. Then we calculate it and create alternative model. Some another interesting class which can be modified by two exocyclic heteroatoms. For example, sulfur atom and nitrogen atom is triazopteons. They can be synthesized from the ester, which from this ester. At the first state, it's condensation with carbon sulfide in the presence of base and then more reaction with hydrogen hydrate. And then we modify this by different aldehydes in the presence of acetic acid, then alkylate. I think in chemistry we can find a lot of works in chemistry of 1 to 3 triazoles. I think you know some articles of Sharpless. I think he's a very famous scientist nowadays. His concept of click chemistry was realized in our work too. For example, we synthesized these molecules which contain 1 to 4 triazoles and 1 to 3 triazoles systems. By the first stage, we calculate 1 to 4 triazole by alkyl halogenate. And then we condensate it with organic azides in the presence of copper containing catalyst. But it's not so easy for working in this field because of chelating process of copper plus, and we synthesize a lot of complexes, but we want to obtain original organic compound without copper, and we use EDTA for binding copper droplets to plasmid. And we used an alternative way to treat this molecule, which contains three stages. At first stage, we condensate by click chemistry some organic azides with purulins. Then we create some alkyl and at the last stage we alkylate 1,2,4 triazole. We work on this field because we can test our compounds in vitro and some in vivo. Let's see how our model is working. We test in our compounds versus phytopathogenic fungi, for example, some fusariums, rhizoctonias, venturia, Nequalis, bipolaris, raciniaris, Sclerotium, and some others. It's very common phytopathogenic fungi in Russian Federation. We decided to test our compounds versus these pathogenic fungi. For the reference compound, we used triademetron. You can see the results of inhibition at the this position. If our model haven't failed, you can see that it's not good working compounds, but if we will add substituent, for example, this substituent activity is really more high than reference compound. For example, this compound is more active than triademetron versus 4 types of phytopathogenic fungi, and works really good at concentration, this concentration 30 ppm. This model works with other heterocycle in the middle with oxidizole tails. It's this line of substances is more active than before. But most interesting compounds is diazole tails. You can see that more than 6 compounds are really good and better than triademetron. 1 to 3 triazoles isn't so active. I think it's a problem of this ring. In this slide, you can see more active compounds and some references. For example, triademetron is branched structure, has branched structure, but some lipophilic part is similar to others. You can find a molecular here in the structure of Prochlorus. It's commonly used fungicide. It's commonly used in complex with copper or some other metals in our country. I skip this slide. If we work in field of biologically active compounds, we have to test our compounds versus life, another life. For example, in vivo tests in mice, we test are not so highly toxic, and they are belonging to 5 and 4 and 3 classes of toxicity by OECD. A conclusion. I want to say that this linear model is working. We don't have to create branches. We can work with big effective snakes. My work was carried out with support of young scientists. They're working with me in our university, Mendeleev University. We work in one lab. It's a really big team, and I want to thank every member of my team. Thank you for your attention. Thanks.